going to talk about section 4.2 optimization. So suppose that P is in the domain of F, so this is an X value. Then we say F has an absolute maximum, or sometimes some books call it a global maximum, if Y equals F of P, of Y equals F of P, if F of P is greater than or equal to F of X for all X in the domain of F. That is, that Y value is the largest Y value on the domain, then we call it an absolute maximum. And then likewise, F has an absolute minimum or a global minimum if its Y value is less than or equal to all the other Y values in the domain of F. That doesn't have to be unique, so if you looked at, like, say, Y equals sine X, where you know that a sine curve is going to do this wave thing where it's going to bounce around between 1 and -1 and just keep going, then its absolute maximum over the whole real numbers is 1. That's the largest Y value. Even though it's equal to 1 an infinite number of times, that doesn't matter. It's still the largest Y value. And similarly, -1 would be the absolute minimum for Y equals sine of X on the domain of all real numbers. Now, it'll be subtle sometimes, so we have stated this as absolute or global maximum, and so when you see that word absolute or global, it's kind of like a red flag. But most of the time, you're not going to have it written that way. It won't say find the absolute maximum. It'll just say find the maximum or the minimum. And you'll have to be on the alert and know that, oh, we are in fact looking for the absolute maximum. Now in red you say when we're finding the maximum or minimum of the function. So it's the minimum value or the maximum value of the function. Therefore, your answer must be given as a Y value, not an ordered pair. So this will cost you a point, and you have to distinguish when you're finding a relative maximum, just the largest point in some little region, that has to be given as an ordered pair, but an absolute maximum must be given as a Y value. And if you mix those up, you will lose a point for that. That's on the AP exam. That's not just me. Okay. So some functions on some domains do not have an absolute maximum or an absolute minimum. So it depends on the function, and it also depends on the domain. So as we said, for Y equals sine of X, on the domain -infinity to infinity, it has an absolute maximum of Y equals 1, and it has an absolute minimum of Y equals -1. It doesn't matter how many times that a sign is equal to 1. It doesn't have to be unique that way, but it is the largest Y value. Now I've drawn down here in green a couple of periods, a couple of cycles of that sine curve. If we look at that region between 0 and pi, like we see for part B here, then on that region, you can see, on that domain, you can see that the maximum, the largest value, is Y equals 1, but the minimum there is Y equals 0, because at both 0 and pi, the sine of 0 and the sine of pi are equal to 0, and there aren't any values that are smaller than that. But if we look at an open interval on the left, at 0, that means we're going to have an open circle there, and then at pi over 2, we're going to have a solid dot. So on that interval, the piece of the sine curve we're looking at there does have a maximum value of Y equals 1, but it does not have a minimum value because it never quite makes it to 0, and there is no value right next to 0. There isn't a value that's just bigger than 0. So this is an example of a function on this given domain that does have an absolute maximum but does not have an absolute minimum. Now if we make it open on both endpoints, then we get this piece of the curve here. And now there is no maximum, and there's also no minimum, for the same reason that we saw before. there isn't one largest y value or one smallest y value. So what we see is that to guarantee that we're going to have a maximum or minimum, we need to know two things. We need to know something about the function itself. It's got to be continuous, but we also need to know, to ensure that we're going to have a maximum and a minimum, that we have a closed interval. Now, it's possible to sometimes get an absolute max or an absolute min if we don't have a continuous function or we don't have a closed interval. But to guarantee that we have one, we need both of those things. And that's known as the extreme value theorem, the EVT. So, where can a function have an absolute maximum or a minimum? Well, it could be that it occurs at an endpoint. It could also be that it occurs at a place where you have a horizontal tangent, a relative max or a relative min, or it could also be at a place where you have a corner point or a cusp. So that means we're going to look at places where we have a derivative of 0 or an undefined derivative or an endpoint. So that leads us to, so those are the only places we can get the largest or smallest y value, if it has a largest or smallest y value. So this leads to what's known as the candidate test for absolute extrema on a closed interval. So if we have a function on a closed interval, a continuous function on a closed interval, then we know we're going to, from the EVT, the extreme value theorem, we know that there must be a maximum and a minimum. So what we'll do is we'll first find the critical points. That means we're going to take the derivative, set it equal to 0, find where it's 0 or undefined. Those are what we call critical points, and we're abbreviating as CPs. Then we'll just plug each of those critical points into the function, to the original function, and also plug in the endpoints. That will give us a list of y values, a finite list of y values. Of that list of y values, the largest one must be the maximum, and the smallest one must be the minimum. Now, you'll oftentimes be asked to justify your answer. So if you're doing the candidate test, your work is your justification. So you don't have to write another sentence or anything like you would for a relative max or relative min. Remember, a relative maximum, you're going to have to say that the derivative changes from positive to negative. Or you're going to have to argue using the second derivative test that the derivative at that point is 0 and the second derivative at that point is negative, therefore it's a relative maximum. But in the case of an absolute max or min, just your work serves as your justification, that you've found the critical points and you've evaluated the critical points and the endpoints in the function. Okay. Here's an example. So let's find the maximum and minimum for f of x equals x minus sine 2x on the domain 0 to pi over 2. So we have a continuous function f and we have a closed interval, so there must be a maximum and a minimum. So we're going to use our candidate test. So we're going to take the derivative first. So the derivative of x is 1. The derivative of sine is a cosine. It's a chain rule derivative, so we'll get cosine of 2x and then times the derivative of 2x. We're going to set that equal to 0 and try to solve that. Now there's no places where this is undefined because cosine is defined for all real numbers, so we don't have any critical points that come from an undefined derivative. But if we add that to the other side, we're going to get 2 cosine of 2x equals 1. So we want to know where is cosine 2x equal to a half. Now I'm going to say 2x is equal to, now we're only interested in positive values, and ultimately we want just the values between 0 and pi over 2. So cosine is going to be equal to 1/2 at pi over 3, and also at it'll be down there in quadrant 4, which will be 4 pi over 3. I'm sorry, that'll be 5 pi over 3. And then if we, and that should be enough. If we divide by 2, we're going to get then that x could be pi over 6 or 5 pi over 6, but if our domain just goes from 0 to pi over 2, pi over 6 is the only critical point in our domain. So now we're going to evaluate pi over 6 in the original function. We're also going to evaluate the endpoints. So f of 0 and f of pi over 2. So f of pi over 6 in the original function is going to be pi over 6 minus the sine of 2 times pi over 6 is going to be pi over 3. So that's going to be pi over 6 minus, and the sine of pi over 3 is the square root of 3 over 2. Let's come back to that. Kind of hard to tell exactly what that is. F of 0 is going to be 0 minus the sine of 0, which is just 0. F of pi over 2 is going to be pi over 2 minus the sine of 2 times pi over 2 is pi. Sine of pi is 0, so that's going to be pi over 2. Now we have to figure out which is the biggest and smallest. Well, let's look back at that first one, pi over 6 minus the square root of 3 over 2. Whoops, sorry about that. Now we know that pi is roughly 3.14, so we know that 3.14 over 6 is just a little bit more than 1/2. Square root of 3 is roughly 1.7 over 2. So I'm thinking that the 1.7 over 2 is a little bit bigger than 3.14 over 6. So I think that's going to be negative. This middle one is 0 and this is positive. So I would say then that our minimum value is going to be y equals pi over 6 minus the square root of 3 over 2, and our maximum value is going to be y equals pi over 2. And our justification is the work that we showed there. All right, let's look at the next panel. Whoops. Okay, let me slide this down if I can. So now it gets way tougher, and this is a hard place to look. We struggle with this even in BC Calc that have done this before. So finding an absolute maximum on an open interval, and an open interval could be from negative infinity to infinity, is significantly more challenging because we can't just plug in the endpoints like we did before. So here's the strategy. We're going to still find the critical points. That is, take the derivative, set it equal to 0. Any place the derivative is 0 or undefined counts as a critical point. Now, if there's only one critical point on the domain, then our life is much easier. We'll do our number line thing. So let me pull up my pen here. So we'll look at our number line, and so imagine that we have something like this, and this is our only critical point. We'll check the sign of the derivative, just hypothetically say it goes from positive to negative. Now what that's saying is that on our domain, the function is going to be increasing everywhere to the left and then decreasing everywhere to the right. So that is a relative maximum based on our analysis of the sign of the derivative. But if it's the only critical point on the domain, that relative maximum will be the absolute maximum. And so that's what our argument will look like. We'll do our number line, we'll check the sign, and then we'll say it's a relative maximum because the derivative changed from positive to negative there, period. It is an absolute maximum at y equals that f of the critical point because that critical point is the only critical point on the domain. So it takes a lot of words to say that. Okay? Now, if there are more than one critical point on the domain, you cannot use that argument. To argue that something is the only relative maximum, is not a valid argument. So imagine that we had two critical points. So I'm just going to, let me call them, say, A and B. So here's A and there's B. And suppose it goes positive, negative, positive. Now, what that's saying is that our function is increasing, then decreasing, then increasing. Being a relative maximum does not necessarily guarantee it is the largest value on the whole domain. Likewise, being a relative minimum does not guarantee that that's the smallest y value on the whole domain. So that is not going to be a viable argument. So then what we can do is kind of what I call, and this is a Mr. Street made up name for this, a modified candidate test. Since we can't plug in the endpoints, we'll take the limit as it approaches those endpoints instead. Now, keep in mind, A and B might be negative infinity and positive infinity. But if we find that our limit is smaller than some of the other points that we put on there, the critical points we evaluate, we can still make the case that that critical point that is larger than the limits is the largest y value and therefore is the absolute maximum. And similarly, we can argue that for the minimum. So it gets more complicated. Let's see an example of how this might look. So here's our function, f of x equals 4x cubed minus 2x squared. And so we're going to look for absolute extrema. That's what we call absolute max and mins, is x absolute extrema. So the first example, the yellow one, we have a closed interval domain. So that means we can just use our candidate test. Okay? So that means we can just take f prime of x, which is going to be 12x squared minus 24x, and set that equal to 0. We can factor out our 12x, and that's going to leave us with an x minus 2. So we have 0 and 2 are critical points. Now we're going to evaluate at f of 0 because that's in our domain. We're going to evaluate at f of 2 because that's also in our domain. And we're going to evaluate at our two endpoints, f of negative 1 and f of 3. So this is our classic candidate test. So when we plug in 0 into our original function, we just get 0. When we plug in 2, we're going to get 4 times 2 cubed is 8, minus 12 times 2 squared is 4. So that's going to be 32 minus 48. I think that's a negative 16. When we plug in negative 1, we're going to get 4 times negative 1 cubed is negative 1, minus 12 times negative 1 squared is a positive 1. And so that's going to be negative 4 minus 12, which is also negative 16. And then finally plugging in 3, we're going to get 4 times 3 cubed is 27, minus 12 times 3 squared is 9. So that's going to be 4 times 27 is 108, and 12 times 9 is also 108, and so that's going to be 0. So we look at all the choices, and we see that the largest of all of those is going to be y equals 0. And the minimum of all of those is going to be y equals negative 16. Okay, and our justification is just our work. Okay, now it gets more complicated because now our interval is an open interval from 1 to 3, so we can't plug in the endpoints. So we take our derivative, which we already did. We find the critical points, which we already did, and those are 0 and 2. Now we notice that 0 is not between 1 and 3. So the only critical point on our domain is going to be x equals 2. This makes our life significantly easier. So we're looking now at this region between 1 and 3, and we have 2 is our only critical point. So we can do like we've done before. We can plug a number in between 1 and 2, say 1.5. if I plug in 1.5 into I like to go into the factor derivative, then plugging in a positive 1.5 will make the 12x positive, but will make the x minus 2 negative, and so positive times negative is negative, so that will be negative. Plugging in something between 2 and 3, like say 2.5, then the 12x is still positive, but now the x minus 2 has become positive, so it's become positive to the right. Now, we could say f has a relative minimum at x equals 2 because f prime changes from negative to positive, period. End of that statement. F has an absolute minimum of y equals f of 2 because x equals 2 is the only critical point on the domain. I know that's a lot to say, but that's what you're going to have to do. Now, there is no absolute maximum there because the largest value is going to occur as we approach one of those asymptotes. It doesn't matter, or one of those endpoints rather. It doesn't matter which one because it's not going to be an actual value there. So there is no absolute maximum. Okay, now the next one is the hardest of all because now our domain is open, we don't have endpoints, and we see that we have multiple critical points. So now we're going to do our modified candidate test. We're going to evaluate the function at 0 and evaluate the function at 2. Those are our critical points. Then we're going to take the limit as x approaches positive infinity of the original function, not of the derivative. Don't make that mistake. And we're going to look at the limit as x goes to negative infinity of the original function. Now, if the largest or smallest value comes from 0 or 2, that will be the maximum or the minimum. If one of these limits is bigger than the other in everything out of these choices, or if it's the smallest of all of those choices, then there won't be a maximum or a minimum. So when we plugged in 0, we got 0. When we plugged in 2, we saw in the very first one that was a negative 16. Now, when we take the limit as x goes to infinity of 4x cubed minus 12x squared, we know that the behavior is going to be determined by the highest power of x and its coefficient. And if we put in a huge positive number, think 1,000,000, 1,000,000,000, 1,000,000,000,000, cube it and multiply it by 4, that is going to positive infinity. So that means we don't have a maximum. So there's no way that this can be bigger than the positive infinity. Now, similarly, when you plug in negative infinity, or you take the limit as x goes to negative infinity, the behavior is still determined by the highest power of x and its coefficient. That is going to go to negative infinity. And so there is no absolute extrema on this domain. There's no max, there's no min. And our justification is our work. All right, tough stuff here.